In the past 50 years, society has come to realize that everyday activities are causing the planet to warm to potentially dangerous levels. The role of carbon dioxide that is generated by fossil fuel use is well established. But work led by one researcher, Veerabhadran Ramanathan, has raised awareness that other agents, such as refrigerants, methane and natural gas, and air pollution, like soot particles and ozone and smog, warm the atmosphere significantly. After years of research, the Scripps Institution of Oceanography at UC San Diego climate and atmospheric scientist has further concluded that control of these pollutants can provide a short-term relief to the problem of climate change.
It's my great honor and pleasure to bring you a scientific message of hope. There is a practical and proven way to slow down global warming considerably during our lifetime.
The concept advanced by Ramanathan has emerged as what has come to be called a second front in the war on climate change. It targets what are known as short-lived climate warming pollutants. These include agents such as soot and other forms of black carbon that are clearly visible on smoggy days, the methane emitted by livestock and leaky pipelines, hydrofluorocarbons, or HFCs, that are used as refrigerants, and ozone, which is created when other pollutants are mixed together in the atmosphere. They stay in the atmosphere for a few weeks in the case of soot, to about a decade for methane and HFCs. With air quality measures already in effect in places like California, they can be removed from the atmosphere in a relatively short period of time. CO2, on the other hand, stays in the atmosphere for more than a century. Climate change policy has been mired in a gridlock of politics for nearly 30 years. Now the control of short-lived pollutants has been hailed as a breakthrough.
We think that today's announcement, if we do everything we want to do and intend to do, will be looked back on in years to come as a real turning point in the fight against the effects of climate change.
Madam Secretary, you began your presentation by referring to Benjamin Franklin and his passion for science also, and I would like to briefly begin my presentation by paying tribute to the scientists who have enabled us to in fact come together here today. I know amongst us, I have not seen him yet, is Professor Ramanathan, but also Drew Shindle and others who have been with a team of international researchers, sometimes for years, trying to unravel the complexities of what is happening in our atmosphere on our planet.
The story behind this new approach began in 1975 with a key discovery by Ramanathan, then a young NASA researcher new to the United States.
40 years ago, if you asked about global warming and the greenhouse effect, it meant you were talking about carbon dioxide. But in January in 1975, that was all changed. It was changed by Dr. Ramanathan, who found that a group of molecules called chlorofluorocarbons would be much more efficient molecule for molecule than carbon dioxide in trapping the infrared radiation that's trying to escape from the Earth.
My research is primarily driven out of curiosity, just like most research just do. My focus, passion has been to understand nature. So that's what drove my science the first 10, 15 years. Then it just took me in the direction of understanding how humans are impacting nature.
The area that he chose throughout most of his career has been one that has been extremely troublesome to climate scientists. That's the whole issue of clouds, water vapor, aerosols, and even to this day is problematic in terms of approaching the whole climate science problem. So he's been at the forefront of one of the most difficult and challenging areas and has been a major intellectual leader a force in that domain.
Growing up in Madras and later in Bangalore, India, Ramanathan was a virtually self-taught student, spending many frustrating years in high school and college barely understanding his English-speaking teachers when he spoke only Tamil. He had a brief career as an engineer, working as a supervisor in a plant that manufactured the sealed units in refrigerators.
I worked in that plant, which was supposed to make sure these gases didn't escape. And it was quite frustrating because we didn't know how to do that. I hated engineering, I hated that job. So just out of frustration, I decided to go back to graduate school. It was at the graduate school I finally found my calling.
In the mid-1970s, a few serendipitous turns led him to come back to greenhouse gases, this time not as a plant manager, but as an atmospheric scientist. While at NASA, he discovered the major greenhouse effect of the CFCs that cooled the refrigerators at his former plant. A certain amount of carbon dioxide naturally exists in the atmosphere. Incoming sunlight reaches through the atmosphere, hits Earth's surface, and heats the planet. Then the Earth gives off heat as infrared rays. Certain gases in the atmosphere act like a blanket and trap some of the infrared heat so that not all of it escapes to space. The blanket keeps the planet's surface at sufficiently moderate temperatures to make Earth habitable.
Just like a blanket on a cold winter night keeps us warm, not because it gives any heat to us, it traps our body heat.
The industrial era would see concentrations of CO2 begin to rise faster and faster. The blanket was getting thicker. Ramanathan's work showed that the blanket was an even more efficient container of heat than previously thought, thanks to the outsized influence of relatively sparse CFC molecules.
My numbers suggested that one molecule of this chlorofluorocarbon, which escapes from our refrigerators, has the same warming effect on the planet as 10,000 molecules of carbon dioxide.
The conclusions of the 30-year-old postdoctoral researcher immediately gained him national prominence. The very first media interaction of his career landed him on the front page of the New York Times.
So you can imagine a totally unknown guy, scientist, coming from a village from India, suddenly being interviewed by New York Times. There was a personal euphoria about this because when I was in India, we used to go to the US consular office and read New York Times to improve our English. I never ever dreamt I would be on the front page of this newspaper I used to worship.
After the success of the CFC paper, Ramanathan continued his investigation of global warming. In a 1980 paper in the journal Science, he predicted with co-author Roland Madden that the greenhouse effect of man's fossil fuel use would be observable by 2000. That correct prediction would go on to be cited in 2007 by the IPCC, an international panel of scientists and policymakers that assesses the state of climate. In 1985, he led a study commissioned by the United Nations, NASA, and European agencies that showed that methane, halocarbons, ozone, and other gases were just as important as CO2 for global warming. The narrative of short-lived climate pollutants thus dates back almost 30 years, but it was not yet ready for a public telling. Ramanathan continued his study of how the atmosphere would respond to climate warming pollutants. In the early 1980s, he, along with 4 colleagues, created the groundbreaking and widely used Community Climate Model, developed at the National Center for Atmospheric Research. Ramanathan added climate physics, such as the greenhouse effect of water vapor and carbon dioxide, and cloud physics to an existing weather forecast model, and modified it to portray climate and explore how water vapor and clouds would change in a warmer world. But his work with the climate model made him realize that global-scale observations are needed to verify model predictions. he joined a NASA satellite experiment as principal investigator to answer one of the biggest problems plaguing climate science during the 1980s. Clouds are filled with heat-trapping water vapor, and thus warm the atmosphere. However, the shade they provide cools the planet's surface. Scientists wanted to know which of these two forces was stronger. Ramanathan took part in NASA's Earth Radiation Budget Experiment, an analysis of 5 years of satellite data. A team of NASA and university scientists led by him determined that, in fact, clouds had a net cooling effect. But in a world steadily filling up with heat-trapping gases, he wondered how the greenhouse effect would ultimately play itself out. The end of the 1980s would be a time of transition for Ramanathan, who sought a research center where divergent ideas could come together.
After I became director, we wanted to look at the whole issue of climate and realized that in order to do that, we had to expand the regions that we were talking about. In particular, even though David Keeling was doing the work on CO2 and Mauna Loa, that was not the totality of what was going on in the atmospheric domain. I and others began to look around the country to find the person who could be a leader, intellectual leader in that domain. And everywhere we looked, Ram's name came up to the top, that this person was somebody who had enormous flood of new ideas, had a tremendous drive, knew what was going on. And so if we could somehow capture him and bring him to Scripps, this would be a part of that strategic thrust we were trying to accomplish.
Scripps Institution of Oceanography succeeded in attracting Ramanathan, who joined its faculty in 1990. In the following decade, his pace of discovery would accelerate, and he would undertake some of the most ambitious climate science experiments ever attempted.